this is the fun part of the tutorial. We're actually going to start playing with the FPGAs, but first I want to tell you a bit about what you're going to run on the FPGA. So we're going to talk about the operating system and system software. So the Ariane core implements the RISC-V privilege spec in order to boot Linux. So Ariane was specifically designed for booting Linux, and I'm sure that you could boot other operating systems like OpenBSD, FreeBSD, etc., but it was designed for booting Linux. And essentially, there's a variety of functions that you want to have to be able to boot Linux. They're specified in the privilege spec, and there's 3 different modes of operation: user mode, supervisor mode, and machine mode. And so when you bring up the system, you start out in M mode, you move into supervisor mode, and then you move into user mode. And there's a variety of kind of instructions and such that you need to support for this, and you don't need virtual memory. Today, there's actually a patch for RISC-V Linux without virtual memory, but we have virtual memory in Ariane. And the other thing that we want to have is a device tree configuration, and this describes how the system that you're running on is configured. So the great thing about what we're offering here is that this is a fully open source system stack. The applications you run, you can run open source applications if you like. Linux is underneath those. It's managing the hardware, and it's open source GPL. It then calls via the supervisor binary interface to the Berkeley bootloader in our case, but we're going to be moving to OpenSBI, which is another open source bootloader and firmware. And then that is, mediating direct access to the hardware where necessary. And the hardware itself is also open source. So all of the steps here, you can read them, you can modify them, you can recompile them for the purposes of your research or other use. So what happens when you start up the system? Well, you reset your FPGA, everything's going to start up. And the first thing that happens is that they have what we call the zero-stage bootloader. And so this is going to be copying code from the SD card into memory. So there is going to be a Linux kernel on the SD card, and that's going to get copied into the system memory with the bootloader and so on as one blob. And so there are things to kind of clear registers and the on-chip memories. And the other thing it's going to set up is a device tree blob, but we'll get to that in a moment. Then there is the first stage bootloader. This is BBL in our case. And this is going to set up trap table. It's going to load Linux. And once you get into Linux, then there's page table setup, driver loading, environment preparation, and so on. And then the BusyBox environment. So BusyBox is a simple shell environment where we are going to browse the web in the terminal, and we're going to play Tetris shortly. So the zero-stage bootloader, as I mentioned, has some reset code. It also has bare metal drivers. So when you start up, you're going to see things print to the screen. Those are implemented in the driver in the zero-stage bootloader. It's going to access the SD card. And it's also going to handle what's called the device tree. And so we actually come up with a device tree configuration based on how many cores you have, cache sizes, and so on, which peripherals are available. And those get compiled together into a device tree blob, which is copied from the boot ROM or set in the right place by the zero-stage bootloader. The zero-stage bootloader will then do some basic peripheral setup, like initializing the UART, copy the SD image into memory. And this is all done in a single core so that there's no kind of issues with multiple cores trying to access things and cause problems. The next step is the first stage bootloader. So we took the Berkeley bootloader, BBL, and modified that in a couple of different ways. And then it also sets up a variety of low-level drivers or devices, and it also filters the device tree. So this is an important step to remove information that should be known by the firmware, but that the firmware may not want to be known by the Linux kernel. BBL then activates the other cores, and Linux starts from there. Linux uses the open firmware device tree to figure out what peripherals are there, what do the cores look like, which extensions are available to RISC-V, etc. sets our virtual memory, loads kernel modules, and so on. And then we jump straight into the init process, which is BusyBox in our case. And you'll get to see the shell. And you can see over here, you'll see something similar to this kind of output when you're running. And you can hold your board up in front of the screen and take a picture just like this. So if you want to build the Ariane SDK, you can clone it from the Git repository just there. And similarly to what we've got, you'll kind of do this Git submodule update. And if you already have a RISC-V toolchain, you can make use of the one you've got, or you can run make all, and it will build you a toolchain and set everything else up. So what is in this kind of SDK? You've got a cross-compiler, GCC cross-compiler. There is the bootloader is in this RISC-V PK subrepository, which is the patch version of BBL that we have. And there is build root. So build root gives you a small bootable Linux environment with a shell and the programs that you choose. So there's a kind of package manager for build root, and you can choose which packages you want to have. So in our case, we added Tetris, we added kind of a command line browser for the web as well. And then there's this rootfs folder, and there's a configs folder as well. So if you want to customize build root, we've got some driver fixes and custom drivers. Linux is contained inside the build root, and so you'll make the modifications in there. And so if you go into the build root folder, you can change the configurations for Linux. You can add extra drivers to the devices that you're adding, or you can modify the existing drivers and build those in. If you're adding something new, you can add in the correct flags for that. And when you do this, it will install permanently into the SDK. And once you've kind of done that, you can copy the config out into the configs folder as well. Now, if you want to customize BusyBox to add more packages, you can do that using the BusyBox menu config. It's a similar sort of setup here. And they're generally lightweight versions of the GNU applications. So sometimes you try and run the program, and it might not have all the flags that you're used to, or it might fail because it doesn't have as good error handling as the one in Linux would have. And then the last thing that will happen when you want to set up, not today, but in general, is you'll build the bbl.bin, which you want to copy to the SD card, and then you will partition the SD card. And we've got two different partitions on the SD. The first one has kind of the bootloader and kernel. And then the second partition you can use for what you want. We like to put kind of like a Debian image in there so that you can run GCC and apt install programs and so on. And then you will copy that using DD onto your SD card. And be careful when you run DD. You don't want to overwrite your direct disk. So you can use fdisk to double check and make sure that you're specifically writing to the first partition of the correct disk. But we're not going to do that today. Instead, I'm going to hand off to Alexei, and he's going to tell you about how to run the FPGAs in front of you.